All right, so in this problem, we have a solid disk of unknown mass and known radius r. It is used as a pulley in a lab experiment as shown above. A small block of mass m is attached to a string, the other end of which is attached to the pulley and wrapped around it several times. The block of mass m is released from rest and takes a time t to fall the distance d to the floor. And part A, we want to calculate the linear acceleration of the block in terms of the given quantities. They do mention the radius of the pulley and the mass of the block and things like that, but we haven't learned how to deal with any of those things. So for this problem, you don't have to worry about them. So for part A, we need to think of a kinematic equation that we can use given the quantities that we have. So we're given time and we're given distance d, and we want to calculate the linear acceleration of the block in terms of the given quantities. So we could use this kinematic equation, y equals y naught plus v naught t plus 1/2 a t squared. We're starting at position 0, so we'll get rid of y naught. We're starting at rest, so we'll get rid of this term. And then we're going to end up at position capital D. So we're going to have D is equal to 1/2 a t squared. Now we can just solve for a. So a is going to equal 2 times d divided by t squared. For part B, the time is measured for various heights d, and the data are recorded in the following table. What quantity should be graphed in order to best determine the acceleration of the block? Explain your reasoning. So we did this in the lab, and I'm going to go over the process of determining this again. So usually you will either be given an equation or you will be asked to find an equation like we just did in part A. And so the way I like to set this up is, go ahead and go to a blank page to do this. So we have our equation from part A, d equals 1/2 a t squared. They're asking us what quantities should be graphed in order to best determine the acceleration. Now, if we were to just graph distance versus time, we know we would get a curved graph. But if we write the equation for a straight line here, y equals mx plus b, in our case, we don't have an intercept, so we just don't worry about that. And here we're just going to line up the variables with the straight line equation. So we're going to graph distance on the y-axis. We're going to graph time squared on the x-axis. And then the value that's left is going to be equal to the slope. So this is the best way to use the quantities given to figure out what the acceleration is going to be. So our answer here is we are going to graph the distance versus time squared. So on the grid, we want to plot the quantities determined in B part I, label the axes, and draw the best fit line to the data. So on the horizontal axis, we're going to have time squared, which has units of seconds squared. And on the vertical, we're going to graph distance, which has units of meter. We need to figure out the time squared values from our data. So there's our corresponding time squared values. Next, we need to pick appropriate increments for each axis. If we look at distance, we're going up by 0.5 meter each time, and we have 4 major grid lines that we can use for that. So there's our vertical axis. Our horizontal axis starts at 0.46 and goes up to 1.9 as a maximum, and so we could just use the same increments for the horizontal axis. Now we just need to plot the data. So there's our data points, and the last thing to do is to draw the best fit line. So there's a line that best fits the data. You should use a ruler for this part. So for part 3, we need to use the graph to calculate the magnitude of the acceleration. And from what we did earlier, we found that our slope should equal half of the acceleration. So here we can say slope is going to equal 1/2 a. Therefore, a is going to equal 2 times the slope. So we need to get the slope in order to do this. In order to get the slope, we need to know two different data points. So we're going to have slope is equal to d2 minus d1 over t2 minus t1. As far as picking points to use this, they have to be points that are directly on the line, and you should not pick more than one data point that's given. So for this, I'm just going to pick 2 points that are directly on the line, and they're not going to be data points. So there's my 2 data points. I picked 1.1, comma 1.1, and 0.4, 0.4. And it looks like we're going to end up with a slope of 1 after doing this. So we get a slope of 1 meter per second squared. Then acceleration is just going to be 2 times that value. So we get 2 meter per second squared for the acceleration.